from prom this weekend. And we can, of course, start some of the homework as well. So again, this is page 25. We skipped a couple of pages, going to page 25. Slide 25 if you're using the digital copy. That image, when I pulled it to make it bigger, got a little blurry. Yeah. So we're going to skip over the warm up. We're going to kind of define these two words, independent versus dependent, on page 25. Again, we're talking about two events now. So finding the probability that I'm flipping a coin and getting a heads on the coin, and the probability that I'm rolling a die and getting a 1 on the die. So two events. So independent events, make sure my pen's turned on here. The occurrence of one event does not, and I'm capitalizing that word not, highlighting that word not, because that's important, affect the occurrence of a second event. So affect, change, alter, any of those words you could use. But the occurrence of one event does not change, affect, alter the occurrence of the second event. So whatever happens first has no bearing on what happens next. There's no overlap in the two situations. The first event doesn't change the second event. Those are independent events. So they're totally separate from each other. They're independent of each other. Dependent events, the occurrence of the first event affects, changes, alters, any of those words, if I could spell alters, right? The occurrence of the second event. So the first one, there's no changing. Nothing's happening. Whatever you do with the first event, it's not changing the second event. It's not affecting the second event. It's not altering it. Those are independent events. Dependent events, one event essentially changes, affects, alters whatever is happening with the second event. And I have a little bag here with marbles, and when I was, of course, capturing this image and then I pulled it a little bit, it got a little bit fuzzy, a little bit blurry.
It's okay.
But you can still kind of see, we have a bag of marbles, and in this bag of marbles, there are red, green, and blue marbles. So to kind of think about independent versus dependent, if I have a bag of marbles and I pull out a marble from the bag, I look at it, but then place it back in the bag. That's the left side of this image here. So you choose a green marble, you look at the green marble, and then you place it back in the bag. So I started with 7 marbles. I still have 7 marbles. That is an independent event. So that when I go to draw a blue marble, I still have 7 marbles in the bag. On the right side of the diagram, this is the one that's dependent. So I choose a green marble, but instead of putting it back in the bag, I'm keeping it out and I'm placing it on the side of the bag. So when I go to choose a blue marble, now I have 6 marbles in the bag left instead of having all of the marbles in the bag. So that's called a dependent event because the number in the bag has changed. So that's kind of the difference between a dependent event and an independent event. So the number in the bag has changed. And once that number is changed, then it's called dependent. So whether you pull it out and you place it back in it, then it's independent, or you pull the marble out and you leave it aside. That's when it's dependent. So what we're going to do is we're going to look at some examples and just identify if it's independent or dependent. Most of your homework tonight is identifying if the event is independent or dependent. So most of your homework is kind of thinking what's going on with the question. So if you look at the next page, it says tell whether the events are independent or dependent, and then it does say explain. So we're just going to read through these and kind of decide, does the first event change the occurrence or the happening of the event that goes next? So Michael, I'm going to have you try the first one. Can you read the first part A there? Example 1, part A. Okay, so I have a stack of books over on the side. And Michael, let's pretend that they're all different. So you pick a book from that stack. Does that then change the results of what your friend has to choose from? Yeah. Why? Yeah, because can your friend pick the book you chose now? No, because you're going to pick that book and you're going to read that book. So you don't have as many books left on your bookshelf and your friend can't pick that same book. So this is called dependent. If you choose a book first, there is one less book to choose from. So your friend has one less book to pick from as well. That's dependent. So you pick a book first, you're keeping that book, and now there are less options, one less option for your friend to choose from. That's called a dependent event. So let's look at part B. You roll a number cube and it shows a 2. And I have dice in here. So I roll my die, a number cube, I guess is a fancy way of saying it. And I get a 2. So here's my 2. I roll it again and I get a 5. Well, I got a 4, but let's say I got a 5. Does the fact that I got a 2 on the first time change the fact that I got a 5 the second time? Emma, what do you think? Did the fact that I got a 2 the first time change the fact that I was going to get a 5 the second time? No. So this is called an independent event. You could say your possibilities did not change, or your outcomes, your choices. We'll say your choices did not change. So just because I got a 2 the first time doesn't force my die to then be a 5. I'm just rolling one die, and I'm going to roll that same die again and again and again, and I still have 1 through 6 to choose from. All right, let's look at the second group. We have 3 different questions here. Tell whether the event is independent or dependent. And then again, it says to explain. Mrs. Kane chooses a student at random to present their project. She chooses you first and then chooses Kim from the remaining students. All right, Bill, so I'm choosing you to present a project. I'm going to choose you first and then choose Kim from the remaining students. And then I would choose another person from the remaining students and so on. Bill, do you think that's independent or dependent?
Dependent.
And why would you say dependent?
Because you wouldn't choose the same person to present the same project again.
Exactly. That's a great explanation. So you're not going to choose, I'm not going to choose the same person to present the same project. I have one less student to choose from. So there's one less option. I would not choose that same student again and again and again. So you can see that the number of students left has been reduced by 1. That's called a dependent event. Let's look at number 2. You flip a coin and it shows heads up. You flip a same coin again and it shows tails. Josh, do you think that's an independent event or a dependent event? If I get a heads, will that force me to have a tails the next time when I flip the coin?
I think it's independent, but it doesn't mean that it won't force you to get tails the next time.
Exactly, yeah, and that is independent. So just because you choose a heads doesn't force the fact that you're then gonna get a tails. I'll just say one event does not change the second. Or the first time you flip the coin doesn't change what you're going to get the second time you flip the coin. All right, the last one's a little tricky. 1 out of 25 of a digital camera has a random defect. So they're saying that 1 out of every 25 cameras has some defect. You and your friend each buy one of the cameras. You receive a defective camera. So the question is, if you received a defective camera, is that going to force your friend to also get a defective camera? So just because I get a defective camera, will that force Mr. King to also have a defective camera? No. So it's just random. I mean, I guess he got lucky that he didn't get a defective camera and I got the defective one. It must be. So that is independent. So we're not talking about that we have one less to choose from. We're talking about the fact that it's defective. And just because I get a defective camera, it doesn't force Mr. King to also have the defective camera. I don't know how to write that down. We'll say 1 defect. Does not force the second to be defective. So the second concept we're going to look at today is actually doing some calculations with conditional probability.
This is the best one.
Condition met, and you'll see that the problems, the 2 examples we look at with this are dealing with charts. And you'll have 2 problems in your homework that are like this as well.
So I'm going to give you just a brief kind of formula. Change up the colors so we know we're changing. So we'll say the probability of A given B. And I'm just going to have you read what this says. See that line in the middle? That line means given. And I'll explain this in a second. It'll make complete sense. It'll be good. So this is red. Probability of event A. And this is the big part. Given, I'm gonna put that and highlight it. Given that event B happened. Okay, quick example. For all of you at home, we have 2 students in the classroom. One is Michael, who is male, and we have Emma, who is female. So if I ask you, what is the probability of choosing Emma, given that the student is female? What would be the probability of that? What percentage would it have to be? So if I just ask, what is the probability of choosing Emma? Right now it'd be 50%. But if I say, given that it's going to be a female student, 100%. So that changes the probability, because if it was just a probability of picking Emma, it would just be 50%. But since we're giving that it's a female student, that would be 100%. Would be a quick example of that. A lot of this, we looked at cards too. So we could say, what is the probability of an ace of spades given that it is a spade? Well, that reduces it to now you're only looking at the spades, which is 13 cards, rather than the whole deck of 52.
So it makes it more specific. So like, instead of looking at everything, we're looking at specific group.
Yeah. And it'll make a lot more sense with examples. So this is find the conditional probability, the Eve color, the results of a survey about, that looked like a V to me. That's a Y. Oh my goodness. Eye color. I was like,
That's the why it doesn't fit.
woo, I mean, my eyes, I need to get my eyes fixed. The results of a survey about eye color are shown in the table below. What is the probability that a person who is surveyed, what is the probability that a person who is surveyed has blue eyes? So we're just starting out with regular probability. So the probability of blue, we'll have to add up. Michael, how many total people have blue eyes? There's 44 out of how many total? Out of 200. So you have 44 over 200. And what does that reduce to when you put in a calculator? Awesome. 11 over 50. So next it says, what is the probability that a person who was surveyed was a male with blue eyes? So we want to find the probability of blue eyes given that they're a male. So now this changes the number of total outcomes, where before we were looking at the whole thing, 200. Now, since it's only the males, we're only looking at, what is the total going to be here, Emma? Instead of 200 people we look at, what's the new sample space? If it's only males. 100. Good. We can see that over here. Out of that 100, how many males have blue eyes? 35. Good. So now we have 35 over 100. So that reduced our sample space by half, because now we're only looking at the males. At home, does this make sense? Thanks for your response, Mr. Korn. Wonderful. Okay, what does this reduce to? Yeah, 7 over 20. So let's look at a couple more. The table below shows the status of 200 registered college students. Woo, they already did the work for us. The 200 is going to be our total. what is the probability that a random selected student is, we're gonna look at female. Bill, how many female students are there?
80.
Well, total, so if we go all the way across.
Oh,
40,
120.
good, how many male students are there?
80.
80. 80 female, sorry, 120 female, 80 male. So Bill, what's the probability of female?
120 out of 200.
Awesome. 120 out of 200. And who knows what that reduces to? Yeah, 3/5. That means 3 out of every 5 students is female. Now we're going to look for given. The probability of female given, we put that line down. Oh, if female. Probability of full-time given that it was a female. So now we're only looking in the female row. So Emma, what becomes my new denominator? What's my new total? If it's just the females. 120, very good. And then how many are going to be full-time out of the females? 40, good. And that reduces the 1 over 2. How are we feeling about this? Oh, this one right here. So we're going to look at number 3 right here because it uses the same chart as the above. So now we're going to look at the probability of a male. Michael, what's the probability of a male? Yeah, 80 out to 100, and that reduces to? Good. Now here's how we're going to figure out if we learn conditional probability. Michael, how would we write if given they're a male, what is the part-time student? Probability of a part-time student. So I'm going to write probability of yep. Yeah. And then we're going to use that line to write given. Yeah. So now when we look at this, I'm back up top. We're only looking at the males here. So Michael, what is the part-time? Yeah. Our new total is only going to be 80. And then there's 60 part-time out of that 80. And that gives us 3/4. We doing a couple more? All right, that's it. So if you want to go to Google Classroom, it is Monday. Oh yeah, that's no problem. No problem at all. Is it here? Send to replace.
As he's sending it, you can change the subject.
Oh, gotcha.
You can kind of look to see which ones are independent and dependent. So the first group of problems, you're deciding if it's independent or dependent.
Oh, you do.
I don't know where it's going. I don't know why it didn't go there. We'll go like this.
You're too organized for me.
Well, I should have
I'm
already,
used to chaos.
this is my fault. I should have already had it pulled up. I have the other one pulled up, but not that one. So the first group of problems, you're saying independent versus dependent. There's no work really necessary for them. Third one down.
Okay. So let's do odds real quick. 10 red chips and 5 black chips are placed in the bag. You were choosing 3 chips and not replacing them after they're ordered. Would this be dependent or independent here, Emma, if you're not replacing them? Well, remember, think if you have 15 and then you take one away, now there's only 14, right? So this would be dependent. And then give me a quick reason why. You could put something as easy as chips, number of chips, bag changes. That works. Michael, 3. Bill deals each person 1 card and then gives them a second card. Are these going to be dependent or independent?
Change. I give you a card and not card.
Yeah, so it's going to be dependent, number of cards, deck. Let's look at 5. You draw a card at random, then draw another card without replacing. Emma, if you're not replacing, does the number change? Good. You draw a name from a bag, you return the name, shake the bag, then draw a second name. Michael, if we are putting the name back, is it dependent or independent? Yeah,
Big difference. Return was the part of return.
yeah. Was there a return or was there any change? Number 9, selecting a king from a standard deck of cards, replacing it. It's even italicized and highlighted now, and then selecting the queen from the same deck. Emma, dependent or independent? Good, independent. Okay, let's go down and do some of these real quick. Why don't we do 13 through 16, and I'll call it a day with you guys, okay? What is the probability that a Congress member was a Democrat? Democrat.
The information in the chart shows the total number of Congress members.
So first thing you have to do is we're gonna have to get a total. So if you want to add across, the number in the House would be 233 plus 201 plus 1. So if you add those all up, you'll get 435. The Senate, 49 plus 49 plus 1 plus 1. You add those up, you get 100. So your total is going to be 535. So you have to do that math first. So now it should be pretty easy. Emma, what is the probability that a Congress member was a Democrat?
So this whole chart is considered Congress, because House and Senate, both of those are Congress.
So how many Democrats are in the House, Emma? No, I mean Democrats. Huh? So in the House, yeah, 233 plus the 49, and that's going to be over the total. 535. 233 plus 49. Good. 282. All over 535. And then what does that reduce to? That mess up some.
No, I don't hear you.
It doesn't reduce? No. Well, rock and roll. Good. Next, it asks, what's the probability that a Senate member was a Republican? So now we know that it has to be a Senate member. So we have the probability of a Republican given Senate. Now your new total is going to be the number of senators, which is 100. And Michael, how many Republican senators are there? Yeah, 49. Next, it says, what is the probability that a Democrat was a member of the House? So now we're writing the probability of Democrat given House. There are 435 House members. And then we look at the chart, and there were 233 Democrats.
There. A few problems to finish up on the front and a few problems to